Welcome to the sixth part of our webinar series on linear technology. In this video, we will take a closer look at two key performance features of linear guides: preload and accuracy classes. We'll start by explaining what preload is, how it's applied, and how it affects the performance of linear guides. Then we'll explore the significance of accuracy classes, clarify the role of tolerances, and highlight the main factors that impact precision. At the end of this final video in the current series, we'll give you a brief outlook on what's next in our upcoming webinars. Let's begin with the question, what is preload? In linear motion systems, preload refers to the intentional reduction of clearance between moving components, such as the carriage and the rail, by introducing controlled resistance. This is typically achieved using slightly oversized balls. The result, increased rigidity, improved positioning accuracy, and smoother motion. At the same time, vibrations, noise, and backlash are significantly reduced. Preload in linear carriages is typically applied using balls that are slightly larger than the standard spacing between raceways. This reduces the internal clearance between carriage and rail, thereby increasing preload. The preload level depends on the ball diameter relative to the raceway geometry. Larger balls create more preload, but must still fit within the system's dimensional limits. A small amount of elastic deformation occurs at the contact surfaces, resulting in a tight, backlash-free fit. Higher preload increases system rigidity, but also makes the motion less smooth. There are two basic preload systems. The most common is the interchangeable type, where the preload is integrated into the carriage. Rails and carriages can be replaced independently without adjustment. This simplifies maintenance, inventory, and spare part logistics. The second type is the match set, mainly used by Japanese manufacturers. Here, rail and carriage are precisely matched and must always be used together. This approach is used where high preload and precision are required. Replacing individual components is not possible without compromising system performance. Although preload improves performance, too much can be detrimental. Increased friction leads to faster wear on balls and raceways. Energy consumption also rises, especially with electric drives. Installation becomes more difficult due to higher mounting forces, and component life may be reduced due to internal stress. That's why preload should always match the application requirements. No more, no less. Rigidity describes how well a system resists deformation under load. The stiffer the system, the less it deforms and the more precise its motion. Preload directly increases rigidity. However, design, mounting structure, and alignment are equally important. For dynamic and high-precision systems, high rigidity is essential to meet accuracy requirements reliably. Let's move on to accuracy classes. In linear guides, accuracy refers not only to positioning accuracy, but mainly to geometric tolerances between rail and carriage. These tolerances affect smooth operation, load distribution, and ultimately, service life. Key parameters include rail parallelism, which ensures smooth movement, height, meaning the distance from mounting surface to the carriage reference point, and width, which defines the side fit. Deviations in height or width between multiple carriages on the same or parallel rails must also be tightly controlled to avoid misalignment or internal stress. Even small deviations can cause misalignment, uneven load distribution, and early wear. Especially in systems with multiple carriages or parallel rails, tight tolerances are critical. Accuracy classes ensure that the guide system matches the precision requirements of the application and prevent over or underdimensioning. Most manufacturers offer between 4 and 6 accuracy classes, such as normal, high, precision, super precision, and ultra precision. As the class increases, the tolerances become tighter. While naming conventions vary, tolerance values are generally comparable. Normal class is used for basic automation or positioning tasks. High classes are common in pick-and-place or standard machine axes. Precision and ultra-precision classes are used in measurement, inspection, and semiconductor technology. A common misconception is that higher accuracy compensates for poor mounting. In fact, the opposite is true. The higher the guide's accuracy, the more precise the installation must be. Inaccurate flatness or misalignment can cancel out the benefits of a high-precision guide or even cause damage. In our next webinar series, we will focus on high-precision bearings. We will provide an overview of different bearing types, designs, and applications, as well as selection criteria for demanding uses. We look forward to having you join us again. Thanks for watching, and see you in the next session.